For the better part of a decade, the Chengdu J-20 mighty dragon flew with borrowed power. Its first operational batches used the Russian AL-31F, the same engine that has powered Chinese fourth-generation fighters since the 1990s. Later variants transitioned to the domestic WS-10C, a capable engine, but one that denied the J-20 its full potential. Analysts, military observers, and Pentagon assessments all pointed to the same conclusion. The J-20 with interim engines was a fifth-generation airframe constrained by fourth-generation propulsion. The aircraft had its stealth, its weapons bay, its sophisticated avionics, but it could not supercruise. It could not exploit the full aerodynamic potential of its Canard Delta configuration. The engine was the missing piece. By 2025 and into 2026, that piece has arrived. The Shenyang WS-15 Emei has entered serial production, and with it, the People's Liberation Army Air Force is about to become a fundamentally different instrument of power. To understand why the WS-15's arrival matters, you must understand what made it so difficult for so long, and why Russia, with its decades of advanced jet engine heritage, still cannot solve the same problem. The critical challenge in modern turbofan production is not the compressor, not the fuel system, not the avionics integration. It is the turbine blade. A modern high-performance turbine blade operates at temperatures exceeding the melting point of the alloy from which it is made, surviving only because of microscopic cooling channels that route air through its interior, and because of thermal barrier coatings that form a ceramic insulating layer on its surface. Manufacturing these components with the precision, consistency, and material quality required for a high-thrust military engine is, arguably, the single most demanding industrial challenge in aerospace manufacturing. Russia's Izdeliye 30, designated AL-51F1, has been in development for the Su-27 for over 15 years. As of 2024 and into 2026, it remains in limited prototype production. The Saturn Lyulka plant cannot achieve reliable serial manufacturing of single-crystal turbine blades at the scale required for fleet deployment. Russia's Su-27 program is consequently capped at under 20 units per year, not because of airframe limitations, but because the engine assembly line cannot deliver. China faced the same fundamental challenge. The difference is that China solved it. The WS-15's path to serial production runs through three specific industrial innovations deployed at scale within the Aero Engine Corporation of China, the state-owned enterprise created in 2016 specifically to consolidate China's fragmented engine research and production capabilities into a single integrated organization. First, additive manufacturing at industrial scale. The AECC deployed laser powder bed fusion technology, a form of industrial 3D printing that sinters metal powder layer by layer using a precision laser to manufacture turbine blade cooling channels that cannot be produced by traditional casting methods. Complex internal geometries that would require multiple manufacturing steps and generate significant material waste can now be produced in a single operation with approximately 40% less waste and a prototyping cycle reduced from 18 months to 4 months. The operational implication is not just cost, it is velocity. China can iterate turbine blade designs faster than any competitor using conventional casting can evaluate test results. Second, powder metallurgy superalloys. The WS-15 relies on second-generation single-crystal turbine blades manufactured from domestically produced rare earth superalloys at the Shenyang Liming facility. China's dominance of global rare earth supply chains, the country controls approximately 60% of global rare earth production, provides a material security that Russia fundamentally lacks. Russia's chronic inability to source consistent high-grade nickel alloys for hot section components has been a documented constraint on its engine programs since the 1990s. China has no equivalent vulnerability. Third, vertical integration and automation. The AECC operates what Chinese industry documentation describes as black light facilities, fully automated manufacturing environments that run 24 hours per day without human operators on the production floor. This model eliminates the quality variance inherent in semi-manual assembly, allows continuous production scheduling without shift constraints, and provides data-driven process control that traditional aerospace manufacturing lines cannot match. The contrast with the Russian United Engine Corporation, which relies heavily on legacy semi-manual tooling and a workforce with declining institutional expertise, is not subtle. China has restructured its engine production as a high-volume, data-driven industrial process. Russia still manufactures engines as a skilled craft.
The WS-15 production ecosystem is distributed across three primary nodes in China's defense industrial geography. The first and most critical is AECC Shenyang Liming, Factory 410 in Chinese defense industrial nomenclature, which serves as the primary site for WS-15 final assembly and testing. Liming is the oldest and largest aero engine manufacturer in China, having produced engines continuously since the 1950s. Its current configuration combines legacy manufacturing expertise with modern automated tooling in an integration that reflects the broader AECC transformation. The second node is the AECC Gas Turbine Institute in Sichuan Province, which handles core research and development work on turbine blade metallurgy and thermal management, the component-level science that determines whether serial production is possible at all. The third node is the Chengdu Aircraft Corporation, which performs the final mating of the WS-15 power plant into the J-20B airframe before the aircraft undergoes acceptance testing and delivery to PLAAF units. These three facilities function as an integrated production system, and understanding their relationship explains why China's production ramp-up has followed a trajectory that Western analysts did not anticipate.
The production targets are not classified. They appear in Chinese state media, in analyses by the Royal United Services Institute, in assessments by the Center for Strategic and International Studies, and in annual Pentagon reports to Congress on Chinese military power. The target figure, 1,000 J-20s by 2030, requires the following industrial calculation. China's current J-20 fleet is estimated at approximately 250 to 300 airframes as of early 2026. To reach 1,000 by 2030, PLAAF must commission roughly 750 new airframes across approximately 4 to 5 production years. At current reported production rates of 100 to 120 airframes per year, this trajectory is mathematically achievable, but requires sustained production pace without significant disruption. Each J-20 carries 2 WS-15 engines. 750 new airframes require 1,500 engines at minimum. Apply the standard spare engine ratio for a high-thrust military power plant, approximately 1.5 spare engines per operational aircraft, and the total WS-15 requirement between now and 2030 approaches 3,750 engines. Current production rate estimates place AECC Liming at approximately 80 to 90 engines per month in 2026, scaling toward a projected 120 per month by 2030. The math is coherent. The industrial capacity, if maintained, supports the fleet target. Whether it is achievable depends on one variable that no open-source analysis can fully assess: whether the supply chain for dysprosium and other rare earth magnetic materials required for advanced motor windings within the engine control systems remains uninterrupted.
The arrival of the WS-15 in serial production accelerates a fleet transition that was already underway before the engine solved its development challenges. The J-20's primary replacement targets are the Russian origin and Russian-derived fighters that form the backbone of the PLAAF air superiority capability through the 2000s and 2010s. The Su-27SK, the Su-30MKK, the J-11A, and the J-11B. These aircraft, derivatives of the Sukhoi flanker family, represent a generational capability gap relative to what the J-20 provides. They are fourth-generation platforms with radar cross-sections measured in square meters, without internal weapons carriage, without low absorbency design features, and without the range and persistence that characterize modern air superiority. The eastern and southern theaters, the two PLAAF formations that would be most directly engaged in a Taiwan contingency or a South China Sea conflict, are the priority recipients of new J-20 deliveries. Analysis of brigade-level unit assignments indicates that units previously operating J-11B and Su-30MKK platforms are the first to transition to J-20. The goal, explicitly referenced in Chinese defense planning documents cited by multiple Western think tanks, is to phase out third-generation fighters from frontline anti-access and area denial zones by 2028. The force structure that emerges from this transition is not a Western-style high-low mix. Western air forces pair high-end platforms, F-22 Typhoon, with lower-cost multi-role fighters, F-35 Gripen, to manage acquisition cost and provide mass alongside precision. China's emerging architecture is better described as a high-high model. At the apex sits the J-20B with WS-15, functioning specifically as what one analysis from ZAI describes as a heavy stealth interceptor, a platform designed not for close air support or strike missions, but for hunting the assets that make Western air operations coherent: airborne early warning and control aircraft, aerial refueling tankers, maritime patrol aircraft, and the command nodes that direct precision strike campaigns. Below that sits a second high tier, the J-16 and J-16D, flanker-derived heavy multi-role platforms with enormous weapons loads, electronic attack capability in the J-16D variant, and the range to operate across the vast Pacific distances of a Taiwan or South China Sea scenario. The J-10C fills the rapid response point defense role where stealth is secondary to agility, sortie rate, and weapons load, not a low-capability aircraft, but one designed for a different mission envelope. The J-7, J-8, and Su-27SK are being retired from frontline service entirely, moved to training roles, or decommissioned outright. The era of the flanker as China's primary air superiority asset is ending. There is no J-20E. There will be no J-20E. This is not speculation. It is the operational assessment of every serious Western defense analyst who has examined Chinese export policy for advanced propulsion technology. Beijing has made a deliberate and permanent policy determination. The WS-15 engine and the J-20 airframe that depends on it are classified state secrets, and they will not be exported in any form to any partner during the foreseeable planning horizon. The reasoning is straightforward and operates on two levels simultaneously. At the technological level, the WS-15 contains classified stealth inlet designs, advanced thermal barrier coating formulations, and single crystal blade manufacturing specifications that represent the culmination of 30 years of Chinese aerospace research investment. Exporting this technology, even to a partner as close as Pakistan, creates the risk that the technical secrets migrate through intelligence channels to adversaries who would use them to accelerate their own countermeasures. China's experience receiving Russian technology through official and unofficial channels has given Beijing a precise understanding of how rapidly advanced technical knowledge spreads once it leaves the originating country's control. At the geopolitical level, Beijing recognizes that its most capable export asset is not the J-20, but the leverage that the J-20 generates. By maintaining the J-20 as an exclusively domestic capability, China preserves the strategic gap that makes its air power credible as a deterrent. Exporting the capability dilutes the deterrence.
Nations that have approached Beijing seeking J-20 or WS-15 access, and the confirmed list includes Pakistan, Saudi Arabia, the United Arab Emirates, and Egypt, have been redirected toward lower-tier export platforms. The primary export vehicle for Chinese fifth-generation ambition is the FC-31, rebranded as the J-35 for planned carrier operations and likely to be offered internationally under a J-35A export designation. This aircraft provides genuine fifth-generation stealth characteristics and genuine beyond-visual range weapon capability, but it does not carry the WS-15, does not carry the J-20's range or payload, and does not carry the classified stealth inlet technology that makes the WS-15 integration operationally distinctive. For nations seeking genuine J-20 capability, the answer from Beijing is the same answer it has always been: unavailable. For nations seeking a credible fifth-generation alternative that does not create CAATSA sanctions exposure or Russian supply chain dependency, the J-35A export version is China's offered solution. Whether that is sufficient for the operational requirements of prospective buyers is a different question, and one that differs materially between a nation like Pakistan, whose primary threat environment is India, and a nation like the UAE, whose threat calculus involves Iranian air and missile forces of very different character.
Any nation that proceeds toward acquisition of major Chinese military equipment, regardless of whether that equipment is J-35, J-35A, or any other platform, faces a specific legal exposure under the U.S. Countering America's Adversaries Through Sanctions Act. CAATSA was designed to penalize significant defense transactions with Russia, Iran, and North Korea, but its secondary effects have created a deterrent against large-scale Chinese military procurement for any nation that maintains meaningful economic or defense relationships with the United States. The U.S. Treasury actively monitors defense procurement supply chains for dual-use metallurgy and avionics component transfers that could constitute covered transactions. For a nation like Pakistan, which receives substantial U.S. security assistance and whose military aviation is partially equipped with U.S.-origin platforms, the CAATSA exposure from a large Chinese advanced fighter acquisition is not theoretical. It is a documented constraint that has shaped procurement decisions in multiple countries across Southeast Asia, the Middle East, and North Africa. China understands this dynamic and uses the J-20's non-export status partly to insulate its partners from this exposure. The J-35A, offered at arm's length through commercial export channels, creates less CAATSA surface area than a direct J-20 transfer would. The most analytically significant finding in the technical audit of the WS-15 is not its thrust performance. It is its durability profile relative to Western equivalents. The mean time between overhaul for the WS-15, based on estimates compiled from multiple defense analysis sources, falls in the range of 600 to 800 hours in current production variants. The Pratt & Whitney F-135, the engine that powers the F-35, carries an MTBO of approximately 1,200 to 1,500 hours, with a total engine life of 3,000 to 4,000 hours. The operational consequence of this gap is not abstract. An F-35 fleet of 1,000 aircraft requires a certain number of F-135 engines in the maintenance pipeline at any given time to keep the airframe serviceable. A J-20 fleet of 1,000 aircraft with engines that wear out at approximately twice the rate requires substantially more WS-15 units in production and in storage to maintain the same operational availability rate. This is precisely why the production numbers cited earlier, 3,750 total engines to support a 1,000 airframe fleet, are not an overestimate. They reflect the reality that roughly half the engine inventory at any given time will be in depot maintenance, in transit, or awaiting installation, rather than in operational aircraft.
What appears to be a weakness in durability is, from the Chinese strategic perspective, a deliberate design choice that reflects a specific theory of conflict. China is not optimizing the WS-15 for the same operational environment as the United States. The U.S. Air Force designs engines for sustained operations across a decades-long service life, with extensive peacetime flying hours supporting pilot proficiency and aircraft readiness. The WS-15 is optimized for a different calculus, high performance at the moment of need, with replacement capacity built into the industrial base rather than longevity built into the individual engine. The logic is that in a high-attrition conflict of the type China's military planning envisions, a compressed, high-tempo engagement over Taiwan or in the South China Sea, measured in days or weeks rather than months, aircraft will be lost to enemy action before they approach their engine overhaul intervals. An engine that lasts 600 hours is operationally indistinguishable from one that lasts 4,000 hours if the aircraft carrying it is destroyed in combat after 100 hours of operation. What matters is having enough aircraft in the fight at the moment of decision, not preserving those aircraft indefinitely. China can produce more WS-15 engines than the United States can destroy J-20 airframes if its production rate is sustained and its industrial base is not directly targeted. This is the strategic logic of the disposable engine, and it mirrors the broader Chinese approach to high-attrition warfare that analysis of Operation Epic Fury, the Ukraine conflict, and PLAAF doctrine documents has consistently surfaced.
The WS-15 program, viewed in its totality, is not primarily a story about metallurgy or manufacturing automation. It is a story about strategic intent. A nation that invests 30 decades in solving one of the most technically demanding engineering challenges in aerospace, not for commercial aviation revenue, not for export income, but specifically to give its most advanced fighter genuine supercruise capability and sustained operational range, is communicating something precise about the conflict it is preparing to fight. China has spent a generation building the industrial capacity to produce this engine at scale, the aircraft to carry it, and the doctrine to deploy both in the specific operational environment of the Western Pacific. The WS-15 engine is not a defensive technology. It is not designed to protect Chinese airspace from attack. It is designed to give J-20 pilots the range, the persistence, and the kinematic performance to operate far from Chinese shores, to reach the airborne early warning aircraft that sustain American air operations, the tankers that extend American fighter range, the maritime patrol aircraft that track Chinese submarines, and the command nodes that make American carrier strike groups coherent fighting formations. When the WS-15 engine enters service at scale, the balance of air power in the Western Pacific does not shift, it transforms. This is Strategic Forecast. Subscribe for the next audit of the technologies that are reshaping the world's most consequential military competition.